Geography 243, energy sources, and actually we're going to talk through the first few parts of our diagram 1.1 from the text. So here we're going to discuss energy sources, propagation through the atmosphere, what happens as energy passes through the atmosphere, and then what happens when it strikes the surface of the Earth and ultimately gets reflected or emitted back through the Earth's atmosphere. So when we talk about energy sources, we usually distinguish between passive sources, those which are natural, and active sources, those which are human-made. And so within passive sources, the principal agent is the sun, the solar energy that comes from the sun. But there are other forms of electromagnetic radiation that we receive from the cosmos, and those are always present. Among the active sources, the principal source that we probably have most familiarity with is microwave imaging or radar imaging, which has become fairly common both in meteorology and in Earth remote sensing, vertical Earth radar imaging. Has a lot of uses, particularly because of its ability to penetrate clouds, and so it's very useful in tropical areas and also in high latitudes, in Arctic and subarctic areas where we track things like icebergs, that sort of thing. When it's very cloudy, you need to know where the icebergs are for the purpose of shipping safety and security. And then more and more we see use of laser profilers or LiDAR imaging as a way of also doing imaging of very high resolution imaging of terrain and surface objects, man-made surface objects as well. So this has become much more common. So passive and active energy sources. And so when we model electromagnetic radiation, we use a concept from physics of an electromagnetic wave which has an electric field and then normal to that a magnetic field traveling in a particular direction. And so because electromagnetic radiation travels at a constant speed at around 300,000 kilometers per second, if you have a longer wavelength, then you have a lower frequency. If you have a shorter wavelength, then you have a higher frequency. And so, again, we're working with this model of the visible spectrum, and so the more we can go back and look at this and think through this of what's available to us in terms of the wave model of electromagnetic radiation, this helps us to to understand what exactly we're looking at as we do our work. And so in describing wavelengths, we normally use there are a number of different ways to measure wavelengths. We normally use the micrometer, and so visible ranges from around 0.4 micrometers to around 0.7 micrometers. So it's a very narrow range. And so a micrometer is equal to 1,000th of a millimeter or 1/1,000,000th of a meter. We also use a concept, again from physics, termed a black body, and we use the black body as a construct to describe the hypothetical perfect emission curve for different energy sources. So the most common ones that we look at are the curve, the emission curve, Blackbody curve for the sun, which peaks in the visible in terms of the energy that is available in the radiation that comes to us from the sun, and the Blackbody curve for the Earth, which peaks right about in the thermal, about 8 to 12 micrometers or so, at around 300 at the Earth's ambient temperature, which is around 300 Kelvin, 300 degrees Kelvin. And so as energy begins to pass through the atmosphere, as it strikes the atmosphere and begins to pass through the atmosphere, different things can happen to it, including atmospheric scattering and absorption by different molecular components of the atmosphere. And so as it happens, this scattering and absorption is selective on different wavelengths. So we usually think of scattering as being classed in three different categories: Rayleigh, Mie, and non-selective scattering. Rayleigh scattering principally shorter wavelength from the visible blue out into the ultraviolet. Mie scattering across the visible, and so it appears visibly to us light that has been scattered by these mechanisms as white light. And then non-selective scattering, the principal agent of which is water vapor, both visible water vapor for us in clouds, but also water vapor that doesn't really coalesce and form as clouds. And this also is active all the way across the visible, and so it does appear to us as being white or white light. And so there are some links here that you can look at and get lots more details on the different types of scattering that we've talked about, and also atmospheric absorption. Now, atmospheric absorption, if you think of it, there are different components in the atmosphere that absorb selectively different parts of the electromagnetic spectrum. And so nitrous oxide has a particular curve to it. Oxygen and ozone has a particular curve to it, and each of these curves are percent of the solar or the solar energy that's available, the incoming solar radiation, or insolation as we term it sometimes, the percentage of it that is absorbed by a normal, clear, quote-unquote, atmosphere. And so you have these different components: nitrous oxide, oxygen and ozone, carbon dioxide, and water droplets, H2O. And when you accumulate all these together, all these different components and other less significant components, you get a model of the atmosphere having particular occlusions in it where very little to no energy passes through, and then other places where you have windows through the atmosphere where energy actually will pass through, reach the surface of the Earth, and be reflected back into the atmosphere and then back into outer space. And so, as you can see, the visible is a very small part of this. So as it happens, there is a large atmospheric window through the visible, and there are smaller windows in the infrared. So the solar radiation that reaches the top of the atmosphere, and again, we're looking at this as a function of, in the vertical axis, as a function of energy, and as it passes through the atmosphere, this is actually a generalization of what would reach us, or what might reach us with a clear atmosphere at the surface of the Earth, again ranging through the ultraviolet, the visible, and into the near and mid infrared. And again, you can see the visible, very small part of this package of energy that we have available to us here to illuminate things that are going on. So again, going back, reviewing this, thinking about where we are, now we're at the surface of the Earth. We're down to sea. So what happens at the surface? Well, the really important thing that happens for us is reflectance. And reflectance, we usually discriminate between specular and diffuse reflectance. And so You can have specular reflectance, which is specular, like a mirror, speculum, or you can also have sort of mixed, diffuse, but dominated by specular reflectance. And you always have a larger component, normally, of specular reflectance than you do the types of diffuse reflectance, because we're really almost always interested in diffuse reflectance, that reflectance which is vertical, because that's where we're looking from typically with the instruments that we use. And so, this is something that you have to be aware of as you're looking at reflected energy. You're looking at a model of reflection occurring at the surface that is not constant, depending on the angle that you're viewing the particular reflectance from, right? And so if you think about this, it's logically, when you're looking at an image, you can more or less determine, or you can certainly have some idea of what you're looking at, whether you're looking at vertical diffuse or a higher angle specular reflectance. And so the equation that we use, and this is one of these really simple equations, the equation that we use to model what's happening right at the surface is given by this simple expression. And so the expression reads energy, and each of these terms being modified by the type of energy, whether it's incident energy or reflected energy or absorbed energy or transmitted energy, dependent on a particular wavelength. So this is all specific to a particular wavelength. So incident energy is equal to reflected energy plus absorbed energy plus transmitted energy. And so really the E's all pretty much drop out of this. We know this is energy, right? And the lambda also all pretty much drops out of this, so that the actual specification of this that we're most interested in is I equals R plus A plus T. And as these vary, given us a specific wavelength, then this is really what we're sensing. We're sensing the variability of this incident energy, and how at the surface, right where the solar radiation illuminates what we're trying to see, what happens to it. It's reflected, absorbed, and transmitted in a variable fashion depending on the kind of land cover or land surface that we're looking at. And so we do have these spectral reflectance curves that try to model that variability at different wavelengths. Okay, so when we start doing our remote sensing, we're looking at specific parts of this, and what we find is that different types of land cover change depending on where we're looking in the electromagnetic spectrum. And again, the visible is part of this, but we're also talking about the near and mid-infrared, and even out into the thermal infrared ultimately. And again, here are some more spectral reflectance curves, which are also termed as signatures, largely by older people who work in remote sensing. This is an older term that still is in widespread use in describing these spectral reflectance curves, which we like to think of them as being unique for any given type of land cover. Hence, we would call it a signature. Okay, there we go.